So let's look at problem 10.3. It's a good representative problem of exponential functions. I think there's one very similar to this on the practice quiz, and that means on the next quiz we have, and there's often ones like this on midterms and finals and stuff. So it's a really good basic problem that we should know how to understand. In the next chapter, we'll look at how logarithms can help us do more stuff with this problem. So let's go over this. So they say the number of yeast cells, which very conveniently is represented by the letter y, just like a function is y, so that's nice. The number of yeast cells is 1,000,000, which is 10 to the 6th power, right? 1 with 6 zeros is 1,000,000, times e to the all these numbers, 0.495015 times the time. E you've probably run into before. It's the basic exponential. Its value is 2.71828. We'll talk about why it's such a special number. It's the natural base. It's the natural log is base E. Anyway, it's a very famous number. It's up there with pi. 2.71828 goes on forever. So that's what the base is. And this is a function. So at t equals 0, right? At t equals 0, if you plug in 0 here, anything to the 0 power, including E, is 1. So there are 1,000,000 cells. So we're starting off with 1,000,000 cells at t equals 0. And part A says how many are there when t equals 1. So when t equals 1, the number of yeast cells is 1,000,000, 10 to the 6 times e to just 0.495105, right? Because t is 1, so multiply by 1 and it's just 1. So the trick here is knowing how to use your calculator to plug in e to some power. All calculators are different. The one I like to use, this one here, has a e to the x button, which is the second function of ln, of the natural log, because they are inverse functions. So I plug in this number, 0.495105, and I go second e to the x, and it's 1.64. So that is 1.64 times 10 to the 6th. So it's 1.64, that's this part, and then times 1,000,000. So times 10 to the 6 cells. That's how many cells there's going to be. Started off at 1,000,000, and now there's 1.64 million. You could write this with zeros, put the millions if you don't like scientific notation. But scientific notation saves a lot, right? You don't have to count zeros. Just, 1.64 million cells. Okay? So that's kind of a calculator problem. Part B, what does part B say? True or false, the population of yeast cells will double every 1.4 hours. Okay, well, we got to see, what is the doubling time? So, where should I do this? I'll do this down here. So, B, when will it be doubled? So, at time t, there's this many. Okay, there are y. So the question is, when are there going to be twice as many of that? What time will there be 2y? And there's other ways to look at this too. We could just come up with a number and say, okay, time 0, or let's say at time 1, there's this many cells. At what time are there going to be twice that many cells? When will the number be twice that many cells? That's also one way to do it. So let's try it that way. So this is what we have at time 1. At what time are there going to be 2 times that many? And then we can say what's the doubling time and just subtract them, because that's nice, it's 1 second, right? Or we could also do 1,000,000. We know at t equals 0, it's 1,000,000. At what time will there be 2,000,000 cells? We could do that too. There's lots of ways to do it. Turns out you'll get the same answer every time. And when we talk about logarithms, that becomes more clear. So let's try that one. Let's try, when are there going to be 2,000,000 cells? So 2 times 10 to the 6th, right, that's 2,000,000, is equal to 10 to the 6th e to the 0.495105t. So what time makes this true? When will this thing here be equal to 2 times 10 to the 6th? That's what we want. And then we know the doubling time, because at 0, there's this. At what time, how many seconds until there's twice as many? Okay, well, let's see. What's really nice is that 10 to the 6's cancel. Divide both sides by 10 to the 6, they go away. And we have 2 is equal to e to the this. Now, the way to 2 is equal to e to the 0.495105t. Okay, the way to do this is with logarithms, but they haven't taught us logarithms yet. That's why they say true or false. Is this true? So without knowing anything about logarithms, which you guys probably do, then you can just plug in a number. Okay, they gave us a number which was 1.4 hours. Oh, this is hours, not seconds. So we plug in 1.4 is e to the 1.4 times this, or this times 1.4 equal to 2. So we just check that true or false, right? So let's plug that in. So does 2 equal e to the 0.495105 times 1.4? So we should put a question mark there. Is this the case, right? If they give us that, let's see if that works. So I go on my calculator, 0.495105 times 1.4. I get this number, and I raise that to e dx, and I get that is pretty much exactly 2. 1.9999999. That is 2. So yes, this does equal 2. So the doubling time is 1.4 hours. Again, using logarithms, we could have found that. Here they just say plug it in, see if you get 2 out of it, and we do. So that is true. So that's nice. Again, more or less a calculator problem. Part C says Charlie says he got this formula, big old ugly thing. He says, no, the number of yeast formulas isn't that. The number of yeast formulas of yeast cells. What am I saying? The number of yeast cells is not equal to that. He got that it's still 10 to the 6, which means that t equals 0, it's still a million. But he got this crazy base. Instead of using e, he used base 2.04, that's right, 2727 to the 0.693147 times time. Okay, so that's what he says it is, and the original one we used was y is 10 to the 6 e to the, so I'll just do the same thing, so e to the 0.495105 t. So the question is e to that the same thing as this to this? Okay, so that's what we got to figure out. Are they the same thing? Now, we can write this, so the 10 to the 6 is the same, right? So that's fine. So we just need to see these bases to this the same. So the way you can think about it is this thing here, the one I just wrote, is e to the 0.495105 to the t power, using the rule where if we have a power to a power, you multiply. T, we have a power to a power, so that just multiplies, so you get the t in. And this thing up here is the same as 2.042727 to the 0.6933147 to the t power. Because again, you multiply powers, so we can just put this in and put the power in the outside. So the question is e to that equal to this number to that number? So now again, it's a calculator problem. So did we already do this one? Yes, we did. We already said e to the 0.495105 was 1.64, right? So this number here, because when t equals 1, we already know that this number in here was 1.64. So now we just got to do this. The question is, how do you do that? You got to know how to do that in your calculator. So you raise some number to a power. Mine, it's y to the x button. I put in the space. I go 2.042727. And I go y to the x and plug this in, 0.693147, and that equals 1.64. So it does equal 1.64 also, so they are the same things. They're both 1.64 to the t, 1.64 to the t. So either one would work. So yes. Okay. So that is the way that would work. Okay, so that's the same thing. Again, calculator problems. You have to know how to use your calculator, putting in bases to powers. So figure it out. YouTube it, Google it if you have to. Calculators can be different. but you have to figure out how to do that. All right, and then the last one, D, a third member of your lab working with the same yeast cells took these two measurements. After 6 hours, should you be worried about Anja's results? Are they correct? Does your model overestimate or underestimate the number of yeast cells at time t? So, Anja, a third member of your lab worked with the same yeast cells took these two measurements, 7.2. Okay, so after 4 hours, she got 7.246 times 10 to the 6. I'm going to have to erase this. Okay. So, part D, after 4 hours. So we plug in t equals 4 here. She found, boy, that's a lot of counting. She found out that there's that many cells. She found there 7.246 times 10 to the 6, that many million. 7.246 million. And then after 6 hours, there's more now. There are 16 million, 16.504 times 10 to the 6 cells. So if 4 hours is this many, 6 hours is that many. And should you be worried about her results? If they're correct, does your model overestimate or underestimate? So does this model we have predict these numbers? Or does our model say there's too many or too small? So you just got to plug in. Again, this is a calculator problem. We got to plug in 4 hours and plug in 6 hours. So you take this formula, plug in 4 and plug in 6. Okay, so purely a calculator problem. I'll do the first one. So again, on my calculator, I go 0.495105. And then I go second e to the x. I raise that to the e. Oh, wait, I forgot to multiply by time. Okay, 0.495105 times the time, times 4, right? This times 4 equals this. Then I go second e to the x. I raise it to the e, which is 7.246 about. Oh, that's exactly what I get. So I got 7.246, so that's correct. So the question is, if you plug in 6 there, do you get this number? Or is it too small or too big? And I'll let you try that. Practice plugging that in your calculator and plugging 6 in, plug 6 in here, and see what that is. You don't need to worry about this one, right? That's just the million part. Just does when you plug in 6 equal 16.504? Or is it too big or too small? Okay, so that's kind of the idea with these problems. Again, when we do logarithms, we can kind of do more with them. But this is still pretty cool, figuring out how these things work. Okay, good. Hope that helps.